All right, on to lesson number 3. Our lesson number 3 is introducing some of the key postulates for the foundations of geometry. And this used to be our lesson number 2 last year, and Mr. Murgatroyd did a lovely video for that. So I'm going to pause and let him talk you through the beginning, and then I'll take over at some point. So hold on a second.
So what I'm going to do is just try to talk you through these 5 postulates and just explain them. Some are pretty self-explanatory, others warrant a little bit of explanation. And so again, all of these will be given to you. They'll be on your theorem sheet. It's a theorem postulate sheet, and so there's no need to memorize these. You just need to understand them. Okay, so if we have 2 points floating around in space, if you were to join those with a line, they are joined with exactly 1 line. So 2 points, through any 2 points, there's exactly 1 line. Through any 3 non-collinear points, there is exactly 1 plane. And this was actually something that we alluded to in the previous lesson, in one of the examples in the previous lesson. And so let me jump back to that for just a moment and try to remind you. And so this was the example in which we had points F, G, and H, and we were able to establish that there is a plane that passes through those 3 points, and that is affirmed by this postulate that says through any 3 non-collinear points there is exactly 1 plane. Remember, non-collinear means that the 3 points must not be on the same line. If, of course, we had 3 points that were on the same line, this is not enough to define a plane because it only has 1 direction or 1 dimension, and of course for a plane we need 2. Okay, a line contains at least 2 points. No need really to explain that. It's somewhat self-explanatory and covered by postulate 2.1. Similarly, a plane contains at least 3 non-collinear points, as I explained above. The points must be non-collinear, otherwise we do not have enough information to create the plane. The important thing to understand, though, is when it says at least 3, there could be more than 3. And in fact, of course, a plane contains an infinite number of lines and therefore contains an infinite number of points. Okay, and if we move to the final of the postulates for today, if 2 points lie in a plane, then the entire line containing those points lies in that plane. Of course, that's because planes are 2-dimensional, lines are 1-dimensional, and so if the 2 points are contained within the plane, then all points that lie in that dimensional direction must also be contained within that plane. Okay, and so now we're going to try to apply some of these in what we learned last lesson. For each of these statements, what we're going to try to do is determine if they are always true, sometimes true, or never true, impossible. Under no circumstances could it be true. And so we're going to try to explain the reasoning, and I'll do that with some diagrams. So if 2 lines are coplanar, that means they share the same plane, they will intersect. That is going to be a sometimes true statement. The reason is, so I'm going to draw a representation here of a plane. That plane is going to contain 2 lines, and the 2 lines in this particular case show a very clear point of intersection. But we do have another possibility, and that is, of course, within the plane, we have 2 lines that are coplanar, but those 2 lines are, in fact, parallel to each other, and that would be the instance in which they would nonetheless be coplanar, but they would not intersect. Okay, to the next question. 3 points are non-collinear. That means if you have 3 points, they do not share the same line. This, of course, is also sometimes true. You may have the following instance. You may have a line which contains the 3 points. And so this is an instance in which you can see that the statement is not true. We have 3 points, but they are collinear. And of course, the other example which supports the statement is if 2 of the points were on the line and the 3rd were not. This would be an instance in which the statement is true. This is the instance in which it's false, and therefore we're going to say sometimes true for our conclusion. Okay, if 2 lines intersect, then they are coplanar. And so what I'm going to do is use the diagram from above, this one over here. What we can see is, or hopefully what you can see is, that this is going to be an always true statement. If the two lines intersect, what it guarantees is that there are only two directions or two dimensions, and of course anytime we only have two directions or dimensions, then we have a plane, and so those two lines will be contained within one plane. The counterexample, of course, is if the two lines are not parallel. So in this particular case, we're not considering the parallel option because we've already been told that the lines intersect, and so we can guarantee that they are coplanar. If the lines were not intersecting, we do have an instance where they're coplanar, and we have an instance where they're non-coplanar, but I'm going to show you that in a future lesson. It's something we refer to as skew lines. Okay, and then we come to our part D of example 1. 4 points are non-coplanar, very similar in character to question B. So if we have 4 points, that means they do not lie on the same plane. Of course, we know from one of the postulates above, postulate 2.4, planes can in fact contain an infinite number of points, at least 3, and so we could very easily have the following, where the 4 points that we are referring to are all contained within, let's call it plane X, but we might have a different example where we have 3 of the points defining a plane. So we'll have plane Y, we have 3 points that are non-collinear, so they've got 2 different dimensions or directions. So we've got 2 different dimensions or directions, and then we have our 4th point, which lies above or below the plane, and this is an instance in which 4 points might be non-coplanar. This is an instance in which 4 points are coplanar, and so this statement would be sometimes true. Okay, moving on.
Okay, thank you, Mr. Murgatroyd. Moving on to our first little dose of proof. So we have postulates, we have theorems, we have definitions, but a postulate, sometimes it's also referred to as an axiom. So a postulate is a statement that is accepted as true without proof. We don't need to go through a formal proof, we just know that that's true. So we then use undefined terms, definitions, properties, postulates to make conjectures, which then, once we prove those conjectures, they become theorems. So the only thing that's formally proved are theorems. The process of proof involves the use of deductive reasoning to move from a hypothesis to a conclusion or the conjecture, with each step along the way supported by a justification that is accepted as true. So we use definitions as justifications. We use theorems or postulates as justifications to prove a theorem. So in this course, we will not go through the process of proving all theorems. Some of them we will, because they're interesting. Some of them we won't. And then we'll just use theorems or postulates and definitions to prove other things that are true, not necessarily a theorem. Okay, the first theorem we have that we're introducing you to is called the midpoint theorem. So the midpoint theorem says, if M is the midpoint of segment AB, then segment AM is congruent to segment MB. So again, we use these little hash marks to indicate congruence. Because we have the congruence symbol here, we have the segment symbol on top because it's not an equal to. So we're not talking about lengths, we're talking about the actual physical segment. So the actual physical segment was split in half, therefore this part of the segment is congruent to this part of the segment. Now, sometimes theorems are biconditionals, we call them. If it's a biconditional, that means we can reverse it and it's still a true statement. Or instead of reverse, we call it the converse. So the converse of a theorem is when the hypothesis and the conclusion are interchanged. So for instance, if we use this midpoint theorem up there, if we started with this part, the conclusion, and we made it the hypothesis, if segment AM is congruent to segment MB, then we took the hypothesis and made it the conclusion. Then M is the midpoint of segment AB. So if AM is congruent to MB, then M is the midpoint of AB. Is that true or false? This is the converse of the statement above. This is false. So here's segment AB. I drew M that's not collinear because it doesn't say it's collinear. It just says those two segments are congruent. So converses aren't necessarily true, right? M must lie on segment AB, and I drew it so it wasn't on segment AB. We call that a counter example, right? That's a counter example right here. I drew it up here, sorry about that, but this is a counter example to show that this is in fact a false statement. Okay, if it's a false statement, then it is not biconditional. If it is biconditional, then that means both the theorem, which is the midpoint theorem, and its converse have to be true. Then we would be able to use or combine those by using the words if and only if. However, that is not true. The converse of the midpoint theorem is not true. Therefore, this is not a biconditional. We will have many, many biconditionals as we go throughout the course. And so this is just introducing you to what is a biconditional, so when it comes up in the future, you'll be more familiar with it. Okay, properties of equality and congruence. You learn these hopefully in Algebra 1. Addition property, if you add the same thing to each side, they're going to equal to each other. Subtraction property, multiplication property, division property, substitution. You substitute one thing into the other, and the two original were equal to each other. They're still going to be equal. Reflexive is like reflection, looking at yourself in the mirror. A equals A, B equals B, C equals C. Transitive property, if A equals B and B equals C, then A must equal C. Right? So we will use those in our proofs. So we don't have a lot of time here, so I want to get through a few proofs. Here's an example of a proof. We have a hypothesis. We have some true statement. We're trying to then prove this conclusion. So we have a statement that says JL, segment JL, right here, is congruent to segment KM right here. If that's true, then we need to prove that segment JK, right here, is congruent to segment LM. So first thing you have to do, always step number 1, is to take whatever is given and make that part of your proof, and the reason we know that's true is because we told you so. It's like, we told you so, but it's really, we just write the words given. Then you think about all the things you've learned in geometry and try to apply it. And initially, to get you guys used to proofs, we kind of set up the steps for you, and you're really just thinking of the reason for why that's true. So here we say, okay, well, JK plus KL is equal to what? Remember, we learned that in the previous lesson. If segment JK is plus segment KL, what's that going to equal all together? Well, that's just going to equal segment JL. If we do it over here, if we say segment KL plus segment LM, then that's going to equal what? Well, that's going to equal segment KM. And when we take those two segments that are sharing a common endpoint and add them up, and they equal the large segment, what do we call that? We call that the angle addition postulate, right? In Singapore, we're going to do the AAP, like the CTE and the SCLE and the AYE and all that stuff. So it's the angle addition postulate. Now, if we know that JL is congruent to KM, well, here's JL and KM. So if these two things are congruent to each other, then that means this part here is congruent to this part here because I'm just substituting in this part for JL and this part for KM and writing it on another line. So this is the substitution. The reason this is 2 is because we did substitution. And then finally, our last one, oh my gosh, my pen stinks. Is why then can we say that JK is congruent to LM? Well, look here. Both sides have a KL. If they both have the same thing, what can we do to both sides? We subtract KL from both sides. This is the subtraction property. And that's it. Sorry, continue on the next